Hello guys, welcome to this new video. So this is going to be the first question in the May 2023 Time Zone 1 Paper 2. So here we are told that a ball of mass 800 grams is attached to a string. The distance to the center of the mass of the ball from the point of support is 95 centimeters. The ball is released from rest when the string is horizontal. When the spring becomes vertical, the vertical ball collides with a block of mass 2.4 kilograms that is at rest on a horizontal surface. Alright, so just before the collision, we need to draw the free body diagram of the ball. So, well, first of all, we see that it's 2 marks, so there's a high chance that we're going to need to draw 2 forces as well. This is not always the case, but it's generally a good rule of thumb. But so, well, first of all, the most obvious force is gravity, as since we are on Earth, I assume they didn't mention this, but it would only make sense that this is done on Earth. So we have the gravitational force with G equals 9.81, and we have a tension force that is acting in the rope that keeps the ball connected to the string. And it's important to mention here that here T must be larger than mg, than mg. And the reason this is because here we have this centripetal motion set up, kind of, where the ball moves in this circle of radius 95 centimeters. And since it moves in this circle, there must be a centripetal force. And the centripetal force is provided by the tension force over here. And so for there to be a centripetal force also when it's vertical, the upwards force must still be larger than the downwards force, so that the net force will point towards the center of the circle and will act as a centripetal force. And so these are the only 2 forces that we need to draw. Don't fall into the trap of also drawing a force to the right or something, as just because the ball is moving to the right, it doesn't mean that it has a force acting to the right as well. It just means that at this moment it is not accelerating in the horizontal direction. When it was like a little bit further back, then the gravity acted like this, tension acted like this, and then the tension had a horizontal component which acted as the horizontal force. But when it's vertical, that is no longer the case. And even if we would need to draw a case where it's like this, we would only draw mg and the tension. We would not need to draw the components of a force. We don't draw components on a free body diagram. So these are the 2 forces. And I'm going to show that the speed of the ball is about 4.3 meters per second. Again, right before collision. So the easiest way to do this here is just to consider the energy conservation, as energy always must be conserved. And then we just need to observe what kind of energy transformation is happening here. So we can label this situation 1 and we can label this situation 2. And then we need to consider, well, what type of energy do we have at situation 1? Well, we know that the speed here is 0, so we're not going to have any kinetic energy. So the only energy we're going to have is mgh, the potential energy. And then if we think about block 2, then it's going to have some speed because it's obviously going to strike the block here, so it's going to have E kinetic. And well, I forgot to mention this when we were talking about mgh, but whenever we talk about gravitational potential energy, we always have to choose a height which is going to be a height of 0. So we need to choose our reference height that we will compare every other height to. Here I think it's most logical if we say that this is height equals 0, so where the block is, and so compared to this will have some potential energy. That's why we will have a potential energy up there, and we will have no potential energy in the second case as it's on a height of 0, so mg times 0 will just be 0. So here we have gravitational potential energy converting to kinetic energy. completely. And so we can, and these two must be equal as energy is conserved. So E potential equals E kinetic. Energy before equals to energy after. So we can just write that mg times delta H, change in energy of the block, times 1/2 mv squared. Here the m's actually cancel out, and so the v will just be the square root of 2g delta H. And then if we plug in the values, 2 times 9.81 times the change in height, which was 0.95 meters, and then take the square root, this will give us like 4.32 meters per second, which is indeed approximately what we had to show, like this. And then now we also need to determine the string, the tension in the string, again right before it collides with the block. And I already gave some hints to this when we were talking about the free body diagram, as here we're going to need to have a centripetal force. As if I draw quickly the diagram again, then we know we had this weight, we know we had this tension that was larger than the weight, and we know that we're going to have a net force pointing upwards, as tension is larger than the weight force, and this will be, well, let's just label it F net, like this. And so from this equation we can see that the net force will just be the tension minus mg, as this is how we will have a positive force here. And so we can, well, we know what the net force is. The net force is just the centripetal force, as it's a force pointing towards the center of a circle along which a object is moving. So the object is moving along a circle and there's a force pointing towards the center of the circle, so we just call that the centripetal force. So this is just going to be F centripetal, or we can say mv squared over r. And well, what we had to find was the tension. So rearranging this for the tension will just give us that the tension is mv squared over r plus the weight, like this. And then all we have to do is plug in. So the mass was 0.8, 4.32 meters per second, and then squared 0.95. Here we had to show that the speed was 4.3, but if you want you can use the more precise value. You don't need to, but if you use this value, that's also accepted. So yeah. And also, like, if you couldn't do this part 2, it's like if during the exam you couldn't show that the speed is 4.3, the reason often they include a number here is that if you couldn't solve it, you can still continue on and get some partial marks. So for example, even without solving part 2, you can still fully solve this part 3 and get the 2 marks, as you know that it's about 4.3. So like this, and this was 9.81. This will give us that the tension is 23.6 newtons. All right. Then after the collision, the ball rebounds and the block moves with a speed of 2.16 meters per second. We need to show that the collision is elastic. Well, this is going to be a quite a lengthy question. We can also see this from the marks we can achieve from this, as we need to think about 2 complete steps here. So we're first going to have to find, well, first of all, let's just see what happens. So we have the ball here, it collides with the block, and then the string was something like this. So this was before the collision, and then from this we go into a case where they will hit each other and rebound. So here this was traveling this direction, and after they rebound, the ball will travel to the left and the block will travel to the right. Yes, and so we know that the speed that the ball was traveling with was 4.3 meters per second. So this we can already write in. This was the initial speed of the ball, 4.3 or 4.32. We also know the mass of the ball, 0.8 kilograms. And we also know the speed, the initial speed of this block. Let's call that u2. Well, that was just 0 as it was rest before the collision. It was at rest before the collision. And we also know that the mass of the block is going to be 2.4 kilograms. That was also given to us. And then after the collision, we know that the block will move with a speed, let's call that v2 for final speed, with a speed of 2.16 meters per second. We still know the mass. It's still the same mass, luckily. And then we also know the mass of the ball, 0.8 kilograms. So we don't really know what speed the ball moves with after the collision. And so this is something we should find, as a collision is elastic if kinetic energy is conserved. So that's what we're going to have to check at the end of the day. So if the total kinetic energy is conserved. But for that, well, we already know the amount of kinetic energy we had in before the collision, as it was just the kinetic energy of the ball, because the block had a speed of 0, so no kinetic energy. But after the collision, both items will have a kinetic energy, and we're going to have to add those up and see if that's going to be the same as the initial case. But for that, we need to find the speed of the ball. And the way we can do that is called momentum conservation. Momentum conservation. So this is all, momentum always gets conserved if we're in a closed system, always. So this is not like the kinetic energy and the speed. This will always get conserved even in a non-elastic collision, in an inelastic collision. So we can write up the momentum before and the momentum after, and they should be equal. So we say P before equals P after. So we just have to write down the momentum of each of the items. So P before, the ball had a speed of 4.32. It had a mass of 0.8. And obviously P is just m times v, mass times velocity. So this had this much momentum. The block had zero momentum, as it had a speed of 0. So we can just ignore that. And then in the second case, we know that the block had a speed of 2.16 and it had a mass of 2.4 kilograms. And then the ball will have a velocity to the left, which means that it's going to have a velocity of opposite sign when compared to the block. So it's going to have a negative velocity. So minus 0.8 times the velocity, this v1. And well, if we rearrange for this, then we will find that v1 is just equal to minus, 2.16 meters per second. If you didn't include this minus sign over here, you would have just written plus 0.8 v1, then it would have come out as a negative 2.16, reminding you that it's supposed to go the other way. But since I already accounted for this fact, then it's going to be a positive speed. Alright, so now we are almost done. We know the speed of everything, we know the mass of everything, so we just need to consider whether kinetic energy is conserved or not. So we just write down the E kinetic before. So as I said previously, only the ball had a kinetic energy. So 1/2 times 0.8 times 4.32 squared. This will give us 7.46 joules. And then we look at the E kinetic after the collision. So now we need to consider the kinetic energy of both of our objects. So the ball had a speed of, negative 2.16, but because it's going to be squared, we can just neglect the signs here. And then the mass of the block was 2.4, and it also had a speed of 2.16 squared, and this will be also 7.46 joules. So we conclude that it was elastic, as the kinetic energy was conserved. but the question already asked in such a way to show that the collision is elastic. So the question is already hinting to us that, well, the collision was elastic, so we just need to show it. So if at the end of the question you write down something that shows that it wasn't elastic, then you should start doubting yourself whether you made a calculation mistake or not, because the question wants you to show that it's elastic. The IB is not going to trick you like that, showing you to show it's elastic, but actually it's inelastic. That would be a little bit mean from them. And then we need to calculate the maximum height risen by the center of the ball after the collision again. It's still part of the same sub-question. So again, we can just consider the energy conservations as it was somewhere over here. It rebounded with some speed that we just calculated. And again, the energy conservation is going to hold just like we had in this first part where we had to calculate the final speed. Is the exact same concept. So we can just say that the potential energy gained is equal to the kinetic energy lost. So we just say mg delta h is equal to 1/2 mv squared. Again, the masses cancel out, and so delta h is just 1/2 v squared divided by g. And so that's going to be 2.16 squared divided by 2 times 9.81, which will give us a height of 0.238 meters. So again, just simple kinetic energy just mechanical energy conservation. As at the maximum height, here the speed will be 0, and so at the maximum height we only have potential energy, no kinetic energy. And at the start, if we take the starting point to be height equals 0, then again we have mg times 0, so no potential energy, and we have this much kinetic energy with the speed of 2.16. And then for the last part of the first question, we were given that the coefficient of dynamic friction between the block and the rough surface is 0.4. Estimate the distance traveled by the block on the rough surface until it stops. So, well, first of all, let's look back at what the diagram was like. So we see that at the start we have some smooth surface, so it's not going to lose any of its speed there, but then it goes into this rough surface, which due to friction is going to make it lose its speed. And so we need to calculate how far it can travel before it stops. So I think it's best if we draw a free body diagram first. So this is the block, this is the floor, and then, well, there's the gravitational force acting on it as always, mg, and then we also have a frictional force on the rough surface, as that is what's going to slow it down. Technically you should draw it on the surface like this, but yes. And then we also have the normal force. So these are the forces that we have to work with here, and so we need to calculate the magnitude of this frictional force first, and then we can calculate the distance that it will travel. So we can see that the only force acting in the horizontal direction, so the sum of the x forces, the x components of the forces, is just the frictional force. So this is the net force in the x direction. N and G are only vertical. So we see that F net is equal to the frictional force. And we know that F net from Newton's second law is just m times a. And we know that the frictional force, is also in the data booklet, is the coefficient of dynamic friction in this case, as the block is moving, and then times the normal force. So this is the frictional force, and we know that these two are equal. We know the mass, we know the coefficient of friction, we know the normal force. Normal force is just mg, as we can consider the equilibrium of the vertical forces here. The sum of the y forces must be 0, as our block is not moving up or down. So we can see that n minus g must be 0. So from this it follows that n is equal to mg. So that's how we can replace it. And then if we solve for the acceleration, as that is what we do not know right now, then we will find, we could also cancel out the m's. So we need to plug in a fewer things into our calculator. So this is just 0.4 times 9.81. This will give us 3.924 meters per second squared. And so now we know the acceleration, and we also know the initial speed of the block, as that was given here, 2.16. And we also know that when it stops moving, so when we have to consider the total distance, the final speed will be 0. So we can look at some of the Suvat equations that are in our data booklet, and after some thinking we can see that this formula will be perfectly suitable for us, as we know the final speed, that's 0, we know the initial speed, that's 2.16, we know the acceleration, and we don't know the distance, so that's perfect for us. So we can see that 0 will be equal to u squared plus 2as, like this. So we can just rearrange for s. That will give us minus u squared over 2a, like this. And well, we just need to plug in now. So minus 2.16 squared divided by 2 times minus 3.924. As our acceleration is in the opposite direction to our motion, we are obviously moving this way with the block. Frictional force opposes the direction of the velocity, so it's going to be a negative sign, and that's how these negatives will cancel out, and we'll be left with a positive displacement of 0.594 meters. Alright, so this was the end of question 1 in the May 2023 Time Zone 1 paper 2. I hope this was helpful, and see you in the next question.